Hello guys, this is CodeNCode and this is a video editorial for this problem, beautiful graph taken from Codeforces educational round, and this was rated 1600. So the problem is you are given an undirected and unweighted graph with n number of nodes and m number of edges, and we have to write a number on each edge. The number can be either 1, 2 or 3. We have to write number on each node and the number can be 1, 2 or 3, and the condition is that sum of the numbers an edge, as we know, connects two different nodes, so the sum of the numbers written on those two nodes must be odd. So since an edge connects two different nodes, sum of those two numbers written the numbers written on those two nodes, sum of them must be odd. So we have to tell the total number of calculate the total number of possible ways to write 1, 2, 3 on the graph. So we have to count the total number of ways to assign each node a number 1, 2 or 3, such that if an edge that connects two different nodes, then the sum of the values of those two nodes must be odd. So the question is, how many different configurations are possible? And we have to print the number modulo this number. So as the graph says, there are no self loop or multiple edges, so no node is connected to itself, and between any two nodes there is at max one edge. So if we take an example, so there are two test cases. First test case says 2 and 1, that is there are two nodes, one edge, and the edge is 1, 2. So the graph would look something like this. So if I assign this node value 2, then I can assign 1 or 3 to this node. Reason, if one node is assigned a value odd, then other node must be assigned a value which is even, because sum of odd and even is equals to odd. That is why if you are assigning 2 to this node, then this node must be assigned value either 1 or 3, since those two are odd. So suppose I assign value 2 here, so there are two ways I can fill this node, so there are two possible configuration, plus I can assign 2 here, so there are two possible ways to fill this node. So in total there are 4 different configuration. I can assign 2 here, so 2, 1 or 2, 3, or I can assign 2 here, so it would become 2, 1 and 2, 3. So in total there are 4 possible configuration to fill the values of these nodes. So the answer is 4. For the second test case, the graph would look something like this. This is the second test case. There are 4 nodes and 6 edges, and these are the edges. So the graph is this. Suppose I started to fill values. Suppose I filled 1 here, and if I filled 1 here, then I have to fill 2 here, because these two nodes are connected by an edge. So if this is odd, this must be even. Now since I filled 2 here, this node, since this is even, must be filled with odd number, but this is also connected to this node which is already filled with odd number. So if I fill odd here and odd here, this would go against the condition that we have given, that if an edge connects two different nodes, then their sum would be odd. So if these two nodes are filled with odd values, then their sum is going to be even. So that is not a valid configuration. If you try to fill this graph, you would see that there is no possible configuration to fill the nodes in such a way that it follows all the condition. So the result is actually 0. So the problem is how to determine that the answer is 0 or positive, or how to find the solution basically. So the approach is something like this. If you think about the problem just 2 or 3 minutes, you would understand the problem is basically about bipartite graph. The reason, in the bipartite graph, it is we have to find that if basically that is a bicoloring problem, and if you are filling a node with color 0, then all of the nodes which are directly connected to it must be filled with color 1, or basically with different color, right? And that is what is happening here. If I am filling a node here with color 1 means parity 1. Parity 1 means odd number. If you are filling a node with odd number, then all the nodes which are directly connected to it by an edge must be filled with even parity or with color 0. So there is directly connection between the condition that we are asked to follow and the condition in a bipartite graph. So the graph must be bipartite. If you look at this example, we saw that okay, there is 0 ways to fill this 0 ways to fill values in this graph. That is only possible if the graph is non-bipartite. If you see, the graph contains odd length cycle, which is this length 3. There are more than one odd length cycle there. So, and if you must know the condition of bipartite graph, if there exists an odd length cycle, then the graph is non-bipartite. And since this graph contains odd number of cycles, that is why this graph is non-bipartite, and that is why the solution is 0. So the first condition that we have to test is the graph must be bipartite. Since if you take an example of this, there is no way to fill this as well, because if you fill odd here, then you have to fill even here. If these two nodes are odd and even, then there is no way to fill this node, because this node is connected directly to both of these. So that is why there is no way you can fill this. And this is directly the this graph, as you can see, contains actually odd number of cycle, which means the graph is not actually bipartite. That is why there is 0 ways to fill this graph as well. So the first condition that we have to check is that the graph must be bipartite for the answer to exist, otherwise the result is 0. An important thing to note is that since there can be more than one connected component, so the whole graph must be bipartite. That is, it is not sufficient to check only a single connected component. As you can see, this connected component is not is a bipartite graph. So there is no problem with this, but this connected component is actually non-bipartite, and hence the solution would be 0 for the whole graph. These two connected components are part of a single graph. So since this connected component is not a bipartite, that's why the whole solution of the graph would be 0, because the whole all of the connected component must be bipartite. So we have to test a bipartite condition for each and every connected component. After that, look at this graph. The number of connected components are 2, and both of the connected components are bipartite. So if you remember, each node is given a color in bipartite graph, right? So suppose I have given this node a color 0, this node color 1, this node color 0. So these two nodes are colored with 0, and this node is colored 1. You can give any color to this, doesn't matter. Let's say this is also colored with 0. So the nodes which are colored 0, once you can fill all those nodes with odd number of with odd parity elements, like this and this node you can fill with 1 3 1 3, and this you can fill with odd parity elements. And for the same graph, there is one more configuration, that is for for 0 colored element. Now we can fill 0 color element with value with 0 parity number, and the rest, or the 1 colored nodes, with odd parity. So there, for each graph which is bipartite, there are 2 possible configuration. First, fill the odd colored nodes with odd parity, and even colored node that is colored with 0 with even parity, and the other configuration is just other way around. So how many total number of solution would it contribute? So the total number of configuration would be 2 raised to power, for this graph it would be 2 raised to power 2, because there are 2 nodes which are colored 0. These 2 nodes are colored 0. Each node can be filled in 2 different ways, either by 1 or 3. So there are 2 ways to fill each node. And how many nodes are there? There are 2 nodes of colored 0. So this graph would contribute 2 raised to power 2 into the total result, because this node can be filled in 2 different ways, 1 and 3. This node can be filled in 2 different ways, 1 and 3. And this node, all the even nodes can be filled only by 1 way. So 1 raised to power total number of nodes is actually 1. So it is not going to contribute anything. The result is actually 2 raised to power number of 0 nodes multiplied by 1 raised to power number of 1 nodes. So I'm ignoring the 1 raised to power number of 1 nodes because it is actually 1. So you can only consider this. So this graph is going to contribute 2 raised to power total number of 0 nodes. Now this graph, since there is only 1 node, so this would be contributing 2 raised to power 1 because there is one odd parity node and each node can be filled in 2 different ways. That is why 2 and raised to power 1 because there is only 1 node. So the total for each connected component, the total number of configuration that it contributes into the final result is 2 raised to power number of 0 nodes plus 2 raised to power number of 1 nodes. And this node, if you see, can be filled in 3 different ways. I can fill 1 or 2 or 3. All 3 configuration are valid since this is connected to no one else. So 1, 2 and 3 all possible configuration are valid for this. So this is going to contribute 3 into the final result. And if you apply the same formula to it, since suppose this was zero colored node and 1 colored node in this connected component is 0. So the total number of result would be 2 raised to power 0 plus 2 raised to power 1, which is actually 3. So for each connected component, we are going to check whether the graph, whether that connected component is bipartite or not. Even if a single connected component is not bipartite, the result is going to be 0. Otherwise, we would count the total number of 0 node and total number of total number of nodes colored with 0, total number of node colored with 1. So the result is each connected component would contribute 2 raised to power total number of 0 colored node plus 2 raised to power number of 1 colored nodes. So if let's just start coding. So first let's create some space. Now this is the problem, and there are 3 into 10 to the power 5 number of nodes. So let's take an adjacency list of 3 into 10 to the power 5. Now for each node we must know what is the color of that node. So let's create a color array for each node, visited array for each node, and let's take 0 and 1 to count the for each connected component, to count the total number of nodes colored with 0 and total number of nodes colored with 1. Okay, let's take a array instead. Let's call it C array of size 2. So C of 0 would represent the total number of nodes colored with color 0. C of 1 would represent the total number of nodes in a connected component colored with color 1. So we need n, m, a, b, n number of nodes, m number of edges. I think, oh, there are t test cases as well, so we also need t. While t minus minus, each time we would read n, we would read m, and each time we have to clear the adjacency list from the previous test case. So ar of I dot clear, what we are doing here, clearing the adjacency list from the previous test case. Color, okay, since this is going to be override, so we don't have to reset it. Visited, yeah, visited array, visited of each node is equals to 0, that is this node is also not visited. Now, so after reading n and m, there are m edges. So each time we would read a, b, in the adjacency list of a we would insert b, and in the adjacency list of b we would insert a. So this is adjacency list representation of graph. If you have no idea about this, just go and check out my graph theory lecture series. So now the graph is ready. So now let's say the answer exists. So long int result is equals to 0 and bool flag is equals to true, indicating the answer exists. Now what we have to do, we have to test for each connected component. If ith node is unvisited, this indicates that this connected component is not being visited, or this connected component is not tested for bipartite testing. So in x is actually the code that we would return from bipartite testing function call. So dfs this, and its color say we color this way. So what is happening here, let me explain. For each connected component we would make a dfs call, and that dfs call would return -1 if the graph is not bipartite, otherwise it would return 0. 0 indicates the graph is bipartite. So that is why we are saving it into the into XOR. Let's say it's code. So if code is -1, then the graph is not bipartite, right? And this is the color of that node. But before going into DFS for a connected component, we must set the size of C of 0 and C of 1 to be 0, because before going into the DFS call, in this connected component we have to reset this. The number of nodes in this connected component colored with 0 are 0, and number of nodes colored with 1 are 0 as well. So now if return code is -1, what we are going to do, we are setting the flag to be false, that is the answer doesn't exist, because this graph is non-bipartite, and we are simply breaking out of this for loop. We have to complete the code from there. Just outside of this, if flag is equals to false, which means there exists no answer, so we would print 0, else answer exists, so we would print result, which is this. Now if the code is not -1, so we made a DFS call to test for this connected component. This connected component doesn't return -1, which indicates this connected component is not what we say, it's actually a bipartite bipartite connected component. So if this is bipartite, it would contribute this much. Let's create a function power 2 raised to power C of 0. Let me first write it down. C of 0 plus 2 raised to power C of 1. So what is this? As we have seen, the total number of contribution of a connected component in the result is 2 raised to power number of nodes which are colored 0 plus 2 raised to power number of nodes which are colored 1, right? So this is what is the contribution of current connected component in the final result. But since the result can be very large, this power function we are going to create ourselves. So, and we are also going to create this DFS function, just don't worry. So since the result can be very large, so we have to print it modulo that number, this number, we are going to print it modulo this number. So it is important that we mode result every time after adding 2 raised to power color. So result is equals to result plus 2 raised to power number of node colored with 0. After adding this, perform modulo operation. Again, result is equals to result plus 2 raised to power number of node which are colored 1, and final result. Now let's first create the power function which calculates power of a raised to power b. So it would return int, okay, a raised to power n. It is going to calculate a raised to power n. So long I can take int, but the problem is it is possible that we can get an integer overflow. I just don't want to take any chance, so just result is equals to 1 while n, if n is odd, result is equals to result into a modulo mod n divide equal to, and a is equals to a into a modulo mod. This is modulo exponentiation which calculates a raised to power n in log n time. Finally return result. Okay, now we have to create the dfs function, right? So this I've already explained in the modulo exponentiation I've explained in the number theory series, so if you have no idea, just go check out that. So in dfs, because dfs returns code whether the given connected component is bipartite or not, and C for its color, right? As we reach any node, what we do, we mark it as visited, and since the color of the current node is C, so C of C would be either 0 or 1. So C of C would be incremented since there is a node with this color, so we would increment the count of it, and color of current node is equals to C. This is important to test for bipartite condition. So now after initializing all these things, we are going to traverse the adjacency list of current node. There are two conditions. First, if current node or the child is visited, so visited of child, first condition, let's check, is 0, which means the current child is not visited. So what we are going to do, we are going to make a recursive call to this child, because this child is not visited. So we will make a dfs call to this child and passing the color as this. Now if current node is having color 0, then 0 XOR 1 is going to be 1, that is, it is going to get the different color than the parent. If this is if current node is having 1, then it is going to get 1 XOR 1, which is 0. So either you can write if else condition, if color is 0 pass 1, if color is 1 pass 0, otherwise you can write it this way. So if the recursive dfs call, if the code is equals to -1, simply return -1. Now what is happening here, let me explain first. So if the child is not visited, we are making a recursive dfs call to that child and passing its color. So this dfs returns whether this connected component is what we say is bipartite or not. If it returns -1, which indicates it has found some edge which doesn't follow the bipartite condition, and hence we have to stop and simply return -1, indicating that we have found some edge which doesn't follow the bipartite condition, and hence we are returning -1 without completing this for loop. And otherwise, if the child is not visited, what we would do, if the child is visited, not visited condition is handled here, else, which means the child is actually visited. If the child is already visited, if the child node, this node is already visited, which means it is already colored. So the color of the child node should be different than the color of current node, because these two are connected by an edge. So color of child node and color of current node, if it is same, which means this doesn't follow the condition of bipartite graph, because the node and child are connected by an edge, and if their color is same, which means this is not a bipartite graph, so you will return -1 from here. Otherwise, if the whole for loop executes successfully, then you would reach here, which means the graph is actually bipartite, so you would return 0. So I think everything is fine, and all we have to do, yeah, everything's fine. Just let's test this and see how many errors do we get. It is very unlikely that I write some of the code and it runs without getting any error. Come on. Oh, as I said, this is very unlikely. So let's take the first test case. The result should be 40. Result is 40. Oh, this is working fine in a very first try. That is surprise, believe me. It is very unlikely for me to get the result in a very first try. And I have to remove some piece of code like this. This is only to run on my machine. And this set text function. And a header file windows.h. Everything's fine. Let's submit this and see whether we get any error or not. Most likely we are going to get an error. Let me increase the size so you can see. Running on test 2, and we are going to get an error there. Come on. Oh, really? That's unusual. More unusual than ever. Okay, so we are getting a TLE, and just a second. Okay. Let me see why it may be possible that we are getting a TLE. First of all, NMTAB, okay, NNM. We are clearing all the adjacency list and marking everything as visited, and for each M we are reading A and B in the adjacency list. Okay, this is good. This is good. If it is unvisited, we are initializing them 0, making a DFS call to that node, and then we are breaking, doing this. Everything is fine, at least here. Okay, now for this thing we are marking it visited, incrementing count, setting its color in the adjacency list of this node. If current child is not visited, we are making a DFS call to that child. If the return code is -1, we are returning -1. Otherwise, okay, everything's fine. Now ANN, a raised to power n, while n, which means while n is greater than 0. Oh, sorry, I pasted everything in here. Oh, the problem is this is outside if condition. Sometimes I make this mistake. So if n is odd, then this should happen. This should happen anyways, whether n is odd or not. So this was the error. Let's submit this. As I said, this is very unlikely for me to get the result in a very first try. Again, I need to remove some of the codes. Okay, let's submit it, and in the meantime let's test it. 4 and 0. Okay, this time I think we should get an AC. Running on test case 2 again. This should not get a TLE this time, because okay, this time we have got a wrong answer. Let's see whether this is okay. So I've got the error. The problem is if there are 2 raised to power number of this one and 2 raised to power this one number of ways to fill this single connected component, right? If there are x different connected components, first one can be filled with x1 ways, second can be filled in x2 ways, and third can be filled in x3 ways, then the total number of configuration are going to be x1 into x2 into x3 into dash 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 xn. So total number of ways to fill this connected component are 2 raised to power number of 0 nodes plus 2 raised to power number of 1 nodes, and then after calculating this we have to multiply result with this. So there is no addition in here, it's actually 2 raised to power number of nodes, number of 0 node plus 2 raised to power number of 1 nodes multiplied with result, and result will be initialized with 1. So initialize result with 1, and then the result would be result into 2 raised to power number of 0 nodes plus 2 raised to power number of 1 nodes. So this is the result. This is the total number of ways, total number of configuration to fill this current connected component, and if there are n number of connected components, then the result is going to be multiplied each time with result, is not going to add. So that is what I used the wrong formula, and that is why we got the wrong result. Let's test this. So as you can see 2965 dash 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 689, we are getting almost the same result. This time I don't think we are going to get any problem. Let's simply remove this and remove this extra code which is not needed. The code that I'm removing is actually not needed for this algorithm. It's just extra piece of code that I forgot to remove one extra code. Oh yeah, I've removed everything which was necessary to remove. So this is running currently on test case number 3. The only error, if we get any, is because of integer overflow. If you see here, sign integer overflow, it says sign integer overflow because this and this, the return type of this is long int, so it should not be a problem. Sign integer overflow on line number 36. That is why usually what I do, I take every single integer as long int. Okay, we are getting sign integer overflow here. So let's take every single number as long int. I have defined LLI to be long int, that is why I can replace int with LLI. Now I think this should be fine. This set text needs to be removed. This set text function need to be removed, and this windows.h header file. Usually in live competition I never use, if I have to calculate some power function, that I just don't use simple integer, I use long int. So as you can see, this is running on test case 11, 21, 23 and AC. So we have solved this problem after many approaches. This happens with me many times. Very unlikely that I get the result in the first try. So this was how you solve this problem. I hope you have learned something from this problem, on how to approach the problems, which include, this might have given you some extra idea that how good a problem based on bipartite graph can be. So thank you guys for watching it. If you have any query or suggestion, just post it down in the comments. So thank you guys for watching, and yep, keep coding. Thank you.